Hi, my name is Boris Vasiliev. I am former Associate Professor of Technical University of Sofia, and I worked 10 years for Eurocontrol and European Space Agency in the field of validation of EGNOS system, European Geostationary Navigation Overlay Service. Today we will talk about EGNOS system, and this system is part of so-called augmentation systems. For improvement of the performance of global navigation satellite systems are used at first satellite-based augmentation systems with satellites in orbit which send correction for position determination. The next group is ground-based augmentation system when we use ground stations for navigation corrections. And the third group is aircraft-based augmentation system, ABAS, RAC-RIME, inertials, baro altimeter, baro speed meters, and so on and so on. A satellite-based augmentation system is a system that supports wide area of regional augmentation through the use of additional satellites broadcast messages. Such systems are commonly composed of multiple ground stations located at accurately surveyed points. Today, we use the wide area augmentation system operated by the United States Federal Aviation Administration. The next one is the European Geostationary Navigation Overlay Service, EGNOS, operated by EGNOS System Service Provider on behalf of European Union, GSA. The third one is Multifunctional Satellite Augmentation System, operated by Japan's Ministry of Land, Infrastructure and Transport, Japan Civil Aviation Bureau, and the fourth one is GPS-aided Geo-Augmentation Navigation, GAGAN system, being operated by India. The next one is the GLONASS system, Russian system for diffraction corrections and monitoring, SDCM, operated by Russia. And the last one is the satellite navigation augmentation system proposed by China. On this slide are shown the areas covered by these satellite-based augmentation systems. Here are shown the typical characteristics and requirements of ICAO for navigation when we use satellite-based augmentation systems for navigation. We have several phases or several stages of flight. The first one is en route. The second is en route continental, when we don't fly over the oceans and seas. The third is initial approach, intermediate approach, and non-precision approach, and departure. And the last one, when the requirements are stringent, is approach operations with vertical guidance. And here are given horizontal accuracy, vertical accuracy, integrity, time to alert, horizontal alert limit, vertical alert limit, continuity, and availability. All these parameters are determined by ICAO for different stages of flight. Why we use satellite-based augmentation system? Practically, global navigation satellite systems are very precise systems in comparison with other navigation systems like inertial, like VOR, like DME, and so on. But we haven't confidence in their measurement. We are not sure if we don't use some satellite which doesn't work properly, and in this case the error could reach very big digits, very big amounts. And satellite-based augmentation system improve integrity of this system. That means that the crew of the airplane will be aware within 6 seconds, for instance, that there is something wrong in the proper work of the system. Here is shown a diagram of EGNOS system, European Geostationary Navigation Overlay Service. We have ground segment, which includes at first range integrity monitoring stations, and nowadays we have 39 range integrity monitoring stations, which are spread over the Europe and part of Africa. At first. At second, we have ground segment, which includes 4 master control centers. Nowadays, we use 2 control centers in Rome, Fiumicino Airport, and in Madrid, Torrejón Airport, and 2 additional stations in Germany and England. Instead of these 2 stations, 4 stations, we have a navigation land Earth station, which sent navigation messages for upgrading navigation information and navigation corrections sent by geosatellites. Instead of that, we have GPS constellation, GLONASS constellation, and in the future we will have Galileo constellation and Compass constellation as navigational satellites. These satellites are augmented by 3 geosatellites, which use information from ground and send navigation corrections to the user segments, which includes users of ground, sea, and air. Geostationary satellites lie on geostationary orbit, which is a circular geosynchronous orbit in the plane of the Earth's equator with a radius of approximately 42,000 kilometers measured from the center of the Earth. A satellite in such an orbit is at an altitude of approximately 36,000 kilometers above mean sea level. That means that the satellite rotates with the same angular velocity of the Earth, and all the time the satellites are over given point and with the constant coordinates in WGS, World Geodetic Coordinate System 84. This picture denotes the used nowadays geosatellites, just to see how many satellites used for different purposes, for navigation, for meteorology, for communication, for TV broadcasting, and so on and so on. Practically, for navigation, EGNOS WASS uses up to 3 geosatellites. There are 4 basic system parameters which describe any satellite-based augmentation system: accuracy, integrity, availability, and continuity. They must guarantee that the user is informed on his position with sufficient accuracy and is alerted when the system exceeds tolerance limits. To this aim, horizontal and vertical protection levels are computed, determined by the receiver, to protect users from potential degradation of the system, expressed in terms of horizontal and vertical position errors above a certain user level, called alert limit. This alert limit is determined for aviation purposes by International Civil Aviation Organization for different stages of flight. A situation in which the position error exceeds the alert limit without announcement is called non-integrity event. If protection level exceeds the alert limit, the system is declared unavailable, since in this case the probability of system non-integrity is high. Decision high is specified high above the ground in an instrument approach procedures at which the pilot or crew must decide whether to initiate an immediate missed approach if the pilot does not see the required visual reference, or to continue the approach. This decision height is different for different situations. I have in mind APV1 approach, APV2 approach, CAT1 approach, CAT2, and so on. Example of the different non-integrity definition is shown at this diagram. Practically, we have vertical navigation system error, and all the time satellite-based augmentation system, included our receiver, determines vertical position error. Requirement is all the time vertical position error has to be, protection level has to be higher, bigger than position error. Meanwhile, we have vertical alert limit, as I said, determined by the International Civil Organization, Aviation Organization, and when protection level is lower than alert limit, we have available navigation system. In the case if the protection level is higher than alert limit, the system is unavailable. The case when navigation system error is higher than protection level but lower than alert limit is a case when we have misleading information. And situation when protection level is lower than system error, and meanwhile system error is higher than alert limit, we have hazardous misleading information, very dangerous case. And the last situation, when system error is higher than protection level, but both are higher than alert limit, that means that the crew will be alerted for this situation. We have misleading information and system is unavailable for utilization. Practically, in aviation are used so-called Stanford ESA integrity diagram, focusing on satellite-based augmentation system integrity. Along x-axis, we have, for instance, vertical protection position error. Along y-axis, we have protection level, in our case, vertical protection level, and the most acceptable case will be when all errors, all measurements are above the line determined by the both axis x and y, and in this case the system is available, and we have not misleading information or integrity events. As I explained, the situation when position error is bigger than protection level is called misleading information, and in case when this misleading information is bigger than protection alert limit, we will have hazardous misleading information. Our talk will continue with explanation of EGNOS system service provider with their monthly performances report concerning September characteristics, part of September characteristics for 2015. Here we will see EGNOS characteristic availability performances is the open services availability performance is defined as the percentage of time when the instantaneous horizontal navigation system error is lower than 3 meters and the instantaneous vertical navigation system error is lower than 4 meters over the total number of samples with valid navigation solution. Here is shown for different stations, and we will can see that for Sofia availability equals to 99.73%, and for different stations is different, and we saw that for Central Europe this availability equals to 100%. So the next diagram shows EGNOS approach with vertical guidance once 1 availability. Approach with vertical guidance 1 availability is defined as the percentage of epochs in a month in which the protection level are below alert limits for these IPv1 services. Protection level lower than 40 meters and vertical protection level lower than 50 meters over the total period. And we saw that for Sofia, its protection level is good, higher than 99.9%. But there are regions, these regions are in the border of EGNOS coverage, where the availability is lower than 97%. Here we see the stations, range integrity monitoring station, used for determination of EGNOS parameters. Here are shown EGNOS IPv1 availability for certified airports for utilization of EGNOS approach. This diagram, this figure is shown only to see how many airports in Europe are certified for utilization of EGNOS approaches. And now I will continue with the EGNOS SIS analysis for pseudo-random noise 120 satellite, geosatellites, which is used by European Geostationary Navigation Overlay Service, EGNOS, for Europe, for Burgas Press, where we have a receiver, Novatel OEM4 receiver, for 9th of October 2015. This report constitutes a brief overview of the performance of EGNOS signal in space as observed in Burgas, as I said, over a period of 24 hours from 9th of October. So here is shown the characteristic of this receiver. The latitude, the longitude, the altitude in WGS84 coordinate system, the requirements for IPv1, IPv2 and Cat1 approaches, horizontal alert limit and vertical limits, and determined availability for this airport. As we saw, we have 97.791% for these days availability for IPv1 approach. For IPv2 we have about 82% and for Cat1 11%. That means that we don't satisfy the requirements of ICAO for instrumental approach using EGNOS. Here is shown the type of navigational messages sent by geosatellites and contents of any message. Meanwhile, I want to say that any geosatellite sends any second navigation message, and this navigation message is different type. We use 64 navigation messages, and here are shown navigation messages 1 up to 28 navigation messages, and we see that any navigation message contains different information. For PRN mask, we have to know this navigation message, which satellites concerns. We have fast correction message, navigation message from 2 up to 5, integrity information, fast correction degradation factor, geo-navigation message, time, X, Y, and Z, geo-satellites, almanac, health, and so on. Mixed fax corrections, long-term satellite error corrections. Long-term satellite error correction contains navigation message 25, clock ephemeris coverage metrics, and so on and so on. Here is shown message types over time for Burgas for this day. As we show, there is an interruption in navigation messages caused by different reasons, and these reasons are sent to navigation to users which use this navigation message, and we saw that we have two interruptions in work of PRN120 and one interruption in PRN136 for this time period. Next diagram is very interesting diagram. With blue line, we see horizontal position error. This position error is within 2 meters, even lower than 1 meter. Meanwhile, protection level shown with green line is within 20 meters, from 6 meters up to 20 meters. What is the conclusion? The conclusion is that protection level is too conservative measurement, and this is information which crew knows. Practically, the crew in the air doesn't know information for position error, but it is convinced that the probability that position error is bigger than protection level equals to 10, about 10 in power minus 7. Then that means that we know our protection level. With red line is shown the number of used satellites, number of satellite vehicles which are used. As we show, practically we use satellites from 5 up to 13 satellites, and when we use 5 satellites, the protection level is too high. That means that geometry dilution of precision is very big, and protection level is too conservative because we are not sure which satellites could be used for position determination. We have 3 regions when the protection level is higher, within 20 meters, and we can see that 3 cases are characterized with a low number of used satellite. Despite of this, that we see at least 8, 9, 10 satellites. This is caused by the reason that Burgas is on the border of EGNOS region. Practically, information for all visible satellite, this receiver hasn't. The receiver has information only for satellites which are over Europe and close to the border, but satellites for which are over Russia, over Asia, and so on, and are visible for receiver, are not used by this receiver when this receiver uses corrections received by geo satellites. This picture shows once again information for position error, vertical position error, vertical protection level, and once again number of used satellites, and this number is the same like when we determine horizontal protection level. And we see once again the position error is very low. Despite of this, this vertical position error is a little bit higher, bigger than horizontal position error. Here is shown measured horizontal deviation from reference. We have to have in mind that the coordinates of the antenna used in Burgas is determined with very high accuracy. This accuracy is in WGS, World Geodetic Coordinate System 84. This accuracy is within 2 plus minus 2 centimeters. This accuracy in the position determination of the antenna gives us possibility to determine our error. And this diagram shows our error in horizontal plane, deviation from the reference, from the exact antenna position, and we see this deviation is within 2 meters. In east direction, this deviation is lower than 1 meter. In western deviation, this error is lower than 2 meters, and in northern and south deviation, we have once again error which is in lower than 2 meters. Thank you for your attention.